Consider a lamp that emits 100 joules of light energy every second. That is a power of 100 watts. Now imagine that you place this lamp above a surface so that it illuminates uniformly 10 meters squares of that surface. You could say that each meter square receives 10 joules every second. In other words, that the power received by each meter square is 10 watts. Now approach the lamp closer to the surface. Naturally, the surface receiving the light will be smaller, for example 4 meters square. But it will also be brighter because the light energy received is more concentrated. It would be now 100 watts divided by 4, that is 25 watts per meter square. The brightness you perceive is related to the light power received per square meter. It is a kind of density of energy applied on a surface, and this is what physicists call intensity. The relationship between the amplitude of a wave and the intensity it carries is the following. The intensity of a given wave is proportional to the square of its amplitude. Light is commonly defined as an electromagnetic wave. But what is an electromagnetic wave? And also, what is electric and magnetic about light? A charge placed at a given point in space will generate an electric field around it. The strength of that field at a given position is represented by a vector. The magnitude and the direction of this vector represent the magnitude and the direction of the force that would experience a positive charge of 1 coulomb placed at that position. Now, imagine a metallic bar and focus on one of the electrons in the bar. This electron creates an electric field around it. Then, connect the bar to a source of alternative current. The electron will move back and forth in the bar with the current. It will oscillate. And so will the direction of the electric field the electron generates. This idea is a key point. If you look at how the y component of the electric field strength vector changes with time, it is oscillating, and it can be represented by a beautiful cosine or sine curve. In the second part of the 19th century, Maxwell showed that a changing electric field generates a changing magnetic field and vice versa. So the oscillation of an electric field always generates a magnetic field that oscillates too. Let's go back to our electron. Suppose now that I choose for the alternative current a frequency of oscillation of 10 kHz. This means that the electron oscillates 10,000 times per second. And so does the electric field it generates as well as the induced magnetic field. Imagine now that I place another metallic bar in the oscillating electric field. The electrons in this bar will feel an oscillating force. Yes, they are in an electric field, so they feel a force. They will start to oscillate too. What we did here is we transmitted a signal through space. This is how radio works. Yeah, we have two antennas. The first bar is emitting the signal. The second bar is receiving the signal. When the oscillating electromagnetic field is generated by the first bar, it propagates through space at the speed of light. Yeah, the oscillating electromagnetic field is what we refer as an electromagnetic wave or EM wave. And it is also more commonly referred as light. For example, let's increase the frequency of the alternative current up to 10 trillion Hz. The electron in the bar will oscillate at 10 trillion Hz, and so will the electric field it generates. The resultant EM wave is now infrared radiation. Let's increase the frequency a little more, up to 1 quadrillion Hz. The metallic bar starts to glow now. It emits visible light.
Since we've been able to look up at the sun, we've been aware of light. As darkness is one of very few things that we instinctually fear, we have always bestowed light with godlike properties. But for all of antiquity, we had no idea what light really was. Figures like Newton and Huygens worked with light in the 17th century, but a more sophisticated description of light, which we call classical electromagnetism, was developed largely by James Clerk Maxwell in the 19th century. This theory depicts light as a transverse wave composed of oscillating electric and magnetic fields, which are at right angles to each other and perpendicular to the direction that the wave moves. We will learn more about these fields later. Just like the kinds of waves we have previously discussed, electromagnetic waves have amplitudes, wavelengths, and frequencies. But instead of different frequencies producing different pitches, like sound waves, different frequencies of electromagnetic waves produce different kinds of light. If the light is visible, these frequencies will correspond to different colors. Frequencies greater than this will exist as UV radiation, X-rays, or gamma rays, and frequencies less than this qualify as infrared radiation, microwaves, or radio waves. All of these phenomena are collectively referred to as electromagnetic radiation, and they can be found on the electromagnetic spectrum. Here we can see all the wavelengths and frequencies ranging from radio waves to gamma rays, and we have found some technological use for all of these in modern society. Even though they seem dramatically different, some requiring things like antennas or other equipment to manipulate, all of them are fundamentally the same thing as the light you can see with your eyeballs. They are just of different wavelengths. All electromagnetic radiation moves at the speed of light, which is about 300 million meters per second in a vacuum, the fastest speed possible in the universe. This is fast enough to get from here to the moon in about a second. And since we know that all waves move at a speed that is equal to their wavelength times their frequency, this product will be equal to the speed of light for any type of electromagnetic radiation. How is it that electromagnetic radiation is produced? To answer this question, we have to learn about electric fields. For now, let's check comprehension.
When we make these lenses do this. So let's go find out what they know. Hello, I'm going to ask you a question. Get you to put those two on top of each other. What do you say?
It's getting lighter and it is pitch black.
Whoa, it's me! Hi girls.
Hi.
We're making a video for YouTube for physics.
Okay.
And now, can you rotate one of them like 90 degrees and look at her, look at her through it, and keep rotating, and tell me and describe what you see.
I just see myself, like a mirror.
That's so cool.
And yeah, so what can you see?
Yeah, I can see you and then I can't see
And
you.
then you can't see it,
yeah.
right? So it goes from being pretty see-through
Yeah, and
to
then
being
now.
completely black?
Yeah.
Okay. Do you have any idea of what's going on?
No, none at all.
None at all.
How light can be polarized by sheets of Polaroid. This is a sheet of Polaroid. It's polyvinyl alcohol with iodine thrown in it. So in here, I'm not sure which way round it is, there are long molecules which are stretched out and they conduct along this direction, but they don't conduct that way. So that's what your Polaroid sunglasses are made of, stuff like this, which is built into it. So it reduces the glare, for example, off the road when you're driving along. So I put a sheet of Polaroid on top of this overhead projector, which produces light, and I put another sheet on top, polarized the same way, and they absorb a bit of light for each direction. But if I turn this top one round so that it is actually perpendicular to that original direction, you can see that you can kill off most of the light. So there's some turning backwards, and that's gone all the way around, and now I'm going back again, and you can see that it disappears. This is an offcut, a bit chopped off from the bottom of this to make it a square. And I can put it on top of these two, let me square them up, and you can't see it at all. I can put it underneath these two, and you still can't see it. But if I now slide it in between, you can see I'm rolling this up in the bottom corner and sliding it in between, you see you can see it. If I turn it round this way, it disappears. If I turn it round through 45 degrees, you can see something quite strong, and then turn it round a bit more and it disappears. It's magic. Now you see it, now you don't. Now you see it, What's going on? Well, I find this absolutely fascinating. I couldn't believe this was going to work for...
I'm pretty sure that you already heard that light can be polarized. But what does it mean? What is polarized light? It's an electromagnetic wave. So let's draw a wave. Imagine that this wave is going towards the left. An electromagnetic wave is the oscillation of an electric field. Here you are seeing the wave drawn on the board the way it is because you are facing the board. What about me? What do I see when I look at the board from the edge? I see a wave coming towards me. I see an oscillation in the vertical plane coming towards me. Like my fingers representing a wave coming towards you. You see a vertical plane here with something oscillating coming towards you. Here, the wave of the board is oscillating in the plane of the board and only in the plane of the board. A wave which is oscillating in one plane only is said to be polarized. A polarized wave is represented by a segment with two arrows. You can draw an axis like this. And you see half of the segment is actually the amplitude. The two arrows represent the oscillation. You can represent a wave with the sine curve, and if you want to know where it's going, in other words, its direction of propagation, you can associate with it a velocity vector like this. Or, more simply, you can just draw a line with an arrow. This representation is called a ray, like a ray of light. So when you're looking at a source of light, let's imagine a lamp bulb and your eyes here. You're receiving not one ray, but many rays converging towards your eyes. There is no reason why all these rays correspond to waves all oscillating in the same plane. Some of the waves must be oscillating vertically, some horizontally, and some with an angle. In that case, we say that the light is unpolarized. We can represent this unpolarized light with a cross, and then each tip of the cross there is an arrow. The horizontal double arrow represents the horizontal components of the oscillations, and the vertical double arrow represents the vertical components of the oscillations. In order to transform unpolarized light into polarized light, we need to make it pass through a polarizer. A polarizer is a device which has an axis of polarization. Here I choose it vertical. Only the components of the light which are parallel to the axis of polarization are allowed to pass. So what comes out of the polarizer is light oscillating in a direction which is parallel to the axis of polarization. In other words, the oscillation is within a plane which contains the axis of polarization. The light that comes out of the polarizer is therefore polarized because it's oscillating in one plane only. We have been talking about polarization within the scope of electromagnetic waves. Light, basically. But any transversal wave can be polarized, even mechanical ones. Let me show you an experiment that will give you a reality feel of what is polarization. This is my oven rack. It is made of parallel metallic bars, and it will make a great polarizer. By shaking the cable, I can create a wave oscillating in the horizontal plane, or a wave oscillating in the vertical plane. I can even produce a kind of crazy wave oscillating in many different planes at once. This is our improvised polarizer. I taped some white paper on one of the bars of the rack so that you can see the axis of polarization. I will pass a cable through it and set the axis of polarization horizontal. When I produce a horizontal wave, it's like if there was no polarizer. The wave passes fully. But when I try to create a wave oscillating vertically, Nothing passes. Yes, the vertical wave has no horizontal component, so it is fully blocked. As for the crazy wave, difficult to, as you can see, only the horizontal component passes. I can rotate the axis of polarization, make it vertical. Now it is the horizontal component which is blocked. Only the vertical component passes. Imagine yourself at an exam. You are reading the questions. Explain what is polarized light. Just answer. Polarized light is an electromagnetic wave for which the electric field is oscillating in one plane only. That should do it. Light is an electromagnetic wave. Yes, we perceive the oscillations of an electric field as light. When these oscillations all occur in one plane only, the light is said to be polarized. In this video, we will look at how light can be polarized and what is the effect of this operation on the energy it carries. In other words, get ready to derive Malus Law. Now, let's dive in. Imagine a polarized beam of light for which the plane of polarization is making an angle theta with a vertical. This beam of light is going towards a polarizer, which has an axis of polarization which is vertical. So having a plane of polarization like this means that the oscillations of the light are within this plane. I could try to represent them kind of like this. You see, I represent here the double arrow. That is the incident light in the polarizer. What passes through will be the component of this incident light, which is parallel to the axis of polarization of the polarizer. So this, in red. Therefore, what comes out will be oscillating in a plane which is containing the axis of polarization, so this plane. Now, we can have a better perspective if we position ourselves in front of the polarizer. So I will make another drawing here. By taking an observer position which is facing the polarizer, this is what we get. The green double arrow here is the light going towards the polarizer, and the polarizer is between this light and the observer position. So when this green light passes through the polarizer, only the component parallel to the polarization axis of the polarizer will pass. So this, in red, which is the light coming out here. Now the oscillation is in a plane that contains this axis. When we represent a double arrow like this, we are also representing the amplitude being the length of half of it. So here this is A0, the amplitude of the incident polarized beam. And what comes out will be A, the amplitude of the beam that comes out of the polarizer. I recognize a rectangle triangle here with an angle theta. So it's easy to calculate the output amplitude from the input amplitude. A is A0 cosine of theta. Waves carry energy, and this energy is directly related to the amplitude. For example, take this wave and this one. In your opinion, which of these two waves carry more energy? Well, obviously this one, right? Because it has a bigger amplitude. Light is a wave, so light also carries energy. If you want to know how it does this, check this video. What we notice there is that A equals A0 cos theta. Cos theta is between 0 and 1. So if there is an angle between the plane of polarization of the incident wave and the axis of polarization here, meaning if theta is not 0, that means that A is smaller than A0. The amplitude of the output wave will be smaller than the amplitude of the incident wave. Therefore, the energy carried by the output wave will be less than the energy carried by the input wave. I can rewrite this differently. I can write that the intensity of a given wave is equal to a constant multiplied by the square of its amplitude. Let's play a little bit with this equation. I'm going to square both sides. A squared equals A0 cos theta squared. I can develop A squared equals A0 squared cos squared of theta. I'm allowed to multiply two sides of an equality by the same constant. So I can rewrite this, Ka squared equals Ka A0 squared cos squared of theta. And I'm pretty sure that you recognize the terms. Here, this is I, the intensity of the wave coming out of the polarizer. And this is I0, the intensity of the wave coming in the polarizer, giving me I equals I0 cos squared of theta. This is called Malus Law. Let's do a quick exercise for you to get a feel on how to use Malus Law. You have a polarizer here which has an axis of polarization, which is the vertical. You have an incident beam of polarized light for which the plane of polarization is making an angle of 60 degrees with the vertical. The incident intensity is 100 watts per meter square. What is the intensity of the light that comes out of the polarizer? Straight application. I0 is 100. Cos squared of the angle between the axis of polarization and the plane of polarization of the incident light, so 60 degrees. Cos of 60 is 1/2, so that's 100 by 1/2 squared, so 100 by 1/4, so 25 watts per meter square. What about if the incident light is unpolarized? What happens when it passes through the polarizer? For that, we should remember what is unpolarized light. Unpolarized light is just a construct of many polarized rays. In unpolarized light, you can have some waves which are oscillating horizontally, vertically, that add up to some which are oscillating with an angle, and another one, and it's a combination of all this that gives you unpolarized light. So if you want to calculate the intensity of the light that comes through the polarizer, you can use Malus Law. The first thing you realize is that only the contributions which are parallel to the axis of polarization will pass through. So the light that comes out will be polarized with a plane of polarization containing the axis of polarization of the polarizer. What about the intensity? Well, you can consider each of the contributions. Right? You apply Malus Law for each of these polarized rays, sum what you get, and then take the average. The result of such an operation is that if you have an incident intensity which is I0, what comes out will be I equals I0 over 2. Basically, the intensity is cut in half. Before I close this video, let's do a quick exercise that allows you to summarize everything I said in this video. An unpolarized beam of light passes through two polarizers. The first polarizer has an axis of polarization, making an angle of 30 degrees with the vertical. The axis of polarization of the second polarizer is just the horizontal. The incident intensity of the light is 200 watts per meter square. The question is, what is the intensity of the light coming out of the second polarizer? Pause the video, try to do it yourself, and yeah, you don't need a calculator, you can do everything in your head. The light that comes out of the first polarizer will be polarized along the axis of polarization of this polarizer. So the plane of polarization will make an angle of 30 degrees with the vertical and 60 degrees with the horizontal. The intensity coming out of the first polarizer will just be this divided by 2 because the incident light was unpolarized. So here you have 100 watts per meter square. For the second polarizer, you see that the incident beam is already polarized. So you can just apply Malus Law. I equals 100 cosine of the angle between the polarization plane of the light and the axis of polarization. So here 60 degrees. that you square. So that is 100. Cos of 60 is 1/2. 100 by 1/2 squared, 25 watts per meter squared.
So let's take a simple analogy where I have a rope, and as you can see, I'm creating a transverse wave that is aligned in the vertical direction. Now let's say I pass my rope through a picket fence that is aligned in the same direction. What's going to happen? The wave is going to pass through because my transverse wave is aligned in the same direction as my picket fence. We say the angle is 0. But what if I turn the picket fence around 90 degrees? None of my wave is going to pass through to the other end. I'm going to have a flat rope. That's a very simple analogy for polarization. It is simple, however, if in terms of electromagnetic radiation, it becomes slightly more complex. So here is a little animation of the electromagnetic wave, and if you've seen my video on Maxwell, you'll have already seen this. And so what we have here is an electric field and a magnetic field propagating along the x-axis. Now, for our intents and purposes, we're going to be only concentrating on the electric field. So we're going to turn off the magnetic field. As you can see, my wave looks like my rope and it is in the vertical direction. But the reality is you're going to get all sorts of angles coming at the same time. So you're going to get some going in this direction, some coming in that direction, some going to go in all sorts of different directions. In other words, we have all the planes possible for the electric field to be in as it comes towards you. So when we look at this animation, we're only dealing here with only one particular plane of the electric field. So in actual fact, this is already polarized because you only get one plane. You don't get any in the other directions. What I also have is this grid, and this grid is like my picket fence, and my picket fence in this case is aligned in the same direction as my actual electric field. So my electric field is passing through very nicely, thank you very much. But what would happen if I change the angle of my picket fence? You can see the angle here is 0 and the values here are in radians. So if I change the angle, so let's say we are at 90 degrees, in this case, my angle here is approximately pi over 2, and you can see I'm going to get very little signal out. But what happens if I have something in between? Now, if I use my rope analogy, you know that no matter what angle you choose, as long as it is anything but 0 degrees, your rope will always be blocked to some degree. But this isn't the case here. You're going to see I'm going to still get amount of electromagnetic wave passing through, even though my wave here is at an angle. So let's start with what we call unpolarized light. So although an electromagnetic wave, such as light, is a transverse wave and thus has a particular orientation, any light that usually comes off something that we see is because of excited atoms. So that means every atom is transmitting an electromagnetic wave at some sort of random angle. So the light we see has a variety of planes. So that's represented here by my multiple arrows. So we're only looking at a two-dimensional diagram. What will happen if I put a vertically orientated grid or polarizer in its path? Well, obviously these vertical ones here will get through and the horizontal ones will not get through. But what about the angled ones? Well, the angled ones all have vertical and horizontal components, and I'll just choose this one here. So this one here has a vertical component like so and a horizontal component. Similar over here, this one has a vertical component like so and a horizontal component like so. So what's going to happen is only the vertical components get through of all the various planes. And so as a result, we're going to get something that looks like this. Now, the intensity that we get as a result is, if this is the original intensity over here, then the intensity here is going to be half of that intensity. So now what we have is polarized light. So now let's introduce a second polarizer. And now what we'll refer to there is as the analyzer. So the first one becomes our polarizer because it's polarized light, and the second one analyzes the polarized light that comes off it. So we call this the analyzer. Now, if the analyzer is also vertical, what intensity will you have on the other side? Well, that's pretty easy. Since this is all vertical in the first place, they're all going to pass through equally. So you're going to have this same intensity of light passing through. So we're going to get basically the same value. But what if I turn my polarizer around so that it's at 90 degrees? Well, because all of this is vertical and all of this is horizontal, no electric field gets through, and so therefore the intensity here is going to be equal to 0. But what if my analyzer is not at 0 or 90, but at 30 degrees? My light that is coming in, my polarized light, has two components in relation to the analyzer. It has this component here, and it has this component here. Now this component along here is 90 degrees to my analyzer, so we're not going to have that pass through. But this component is going to come through. Now the angle we have here is theta. It's the angle between my polarizer and my analyzer. And because this is the cosine component, the amount of electric field passing through is going to be the original electric field multiplied by the cosine of the angle. Now, the relationship between the electric field strength and the energy passing through, and thus the intensity passing through, is a square relationship. That is, I is proportional to E squared. That means that the intensity we get on the other side of the analyzer is equal to the intensity coming in, and we're going to call this IP to differentiate it from this guy over here. So this here becomes IP, the polarized intensity that's coming in, multiplied by the cos of theta, and this is squared. Now, there is some mathematics behind this particular relationship. I won't go into now. I'll probably leave that for another video. It's certainly not necessary at this stage. So if we then look at the mathematics involved, we know that the cosine of 30 is root 3 over 2, and therefore if we square that, we get 3 over 4. So therefore our new intensity, that is the intensity that we get on the outer side, is equal to the intensity of the value coming in multiplied by cos squared, in this case 30, and of course that means we get 3/4 of IP. Similarly, if I am going to change this to 45 degrees, because cosine of 45 is 1 over root 2, we're only going to get half of that value. At that position, of course, if this is the original intensity, then at this particular position, we're going to get only 1/4 of the original intensity at that position. Since we started with I naught here it's half already, and then of course 1/4 over here because we're getting a half of the intensity drop over here. If I then go to 60, we know that the cosine of 60 is a half, so now I have only 1/4, 0, so we're getting nothing through to the other side.
This is a microwave generator, and it will generate waves which are polarized in one particular direction. And here is a receiver which will receive them. This wave has a wavelength which is 3 centimeters. Now 3 centimeters is about yay long, whereas the light wave is 60,000 times smaller. So if I set up traveling waves, waves coming out of here and ending up over here and not being reflected, then it'll be a bit simpler. So I'll detect this by turning this on and getting a very nice big signal. Now I pick up a sheet of Polaroid. This is my sheet of Polaroid. It's just long conducting wires, the same as were in those sheets of Polaroid, but you couldn't see them there. So now I put it in this way round, and you see that you don't get any signal, and I turn it around, and I get a huge signal on the meter at the back. So there it is, nothing gets through, and I turn it round slowly, and you suddenly see the signal appear, and when it's perpendicular, I get a really big signal on the screen over there. What's happening here is that this is sending out waves which are oscillating with an electric field that goes up and down in this direction. And as the electric field hits this conducting wire, it induces a current in here, and because of the resistance of the wire, this causes the electromagnetic wave to be absorbed and heat to occur in the wire. So it gets totally absorbed by the wire. If I turn it round this way, well, now the electric field causes a little bit of current to go across there, but then it hits the other side of the wire and it doesn't dissipate any energy, it just gets stored there as a capacitance. So this does not absorb nearly as much energy, and so I get quite a large signal. And then I turn it round there and I get virtually nothing. Now I want to turn this around to show you that they're completely polarized oppositely. So if I have that vertically, this is now giving an electromagnetic wave which is oscillating vertically. This is now detecting only those waves which are going horizontally. It's just like those two sheets of Polaroid there. So I have a wave which is coming out and oscillating this way, and this one is not tuned to detect it at all, so I get no signal. Now I put the sheet of Polaroid in, and there's nothing there. If I turn it to 45 degrees, I get a huge signal going through. If I now turn it round to perpendicular, I get nothing. So I'll start off vertical, there's nothing there. I turn it round, I get a lovely big fat signal coming about 45 degrees, and then when it goes further round, it decays away to 0. So something is happening if I put this in at 45 degrees. I'm able to get waves which are oscillating this way to go through here and be detected by something which is detecting waves that way. I'm changing this signal, which is oscillating this way, to one that's oscillating that way. Otherwise, nothing would go through.
How have you done it?
Well, I haven't done it. It's this sheet of Polaroid that's done it. So if I imagine this as a wave which is coming out and has a vertical polarization like this, I can think of that as partly this angle, this side of the set square, plus that one. So as I put it in at this angle, if I think of this as being vertically polarized up and down, it's partly this and partly that. So as I put that in there, the bit which is running this way along this wire is killed off, and the bit which is running that way is now allowed to continue. So I have a state which is oscillating this way now, and this thing has managed to turn the plane of polarization of this wave from vertical to this direction. And now when this wave travels along this way, part of that is horizontal and part of that is vertical, and the horizontal part goes in. So I have a wave, I measure it, it changes the state of the system from being vertically polarized to one polarized in this direction. Once I've done that, this state can be detected by that. That's the interpretation of this whole experiment. And that's the classical interpretation in terms of electromagnetic waves. Now, Brady, this is the bit that really is going to do your head in, which I'm going to enjoy for the next few minutes. Out of this apparatus comes one photon. It is a photon which is oscillating this way. The chances of the photon going through here are 50-50. It can either be going this way or that way, and if I do it at 45 degrees, they're equally probable. Then you get to this detector, and now it's coming out with that polarization. The chance of going this way are 50-50. So I'm going to only get a quarter of the signal going through if this really works. And that's the explanation why the signal's gone down. But notice now, as this photon comes through, I have to talk about probabilities of what goes on. It is not deterministic. And if you go through the mathematics, you'll find that these states, which I would like to represent using a ket, which is a triangle like this, and you put the symbol in as a triangle, that ket state changes from one to the other. And in here, in between, I have a mixture of two different states, and it's the mixture of these two states that allows me to interpret this experiment. So it's much harder for poor old Brady to understand, because somehow quantum mechanics is biting him on the backside here, and he really doesn't like me to talk about mathematics at all. But without that, and without the idea of splitting this into two different states added together, I have no explanation.